Oh yes, your minor is on Sunday morning, 8 o'clock. So same place where you had your quiz. Syllabus? We'll leave out the two components.
Chapter.
What is that? Yes. So single components. Parts of chapter 6, which okay, there are some things which the other group has done and we've not done. Just a couple of small topics. I'll do that today, right? So that we are both the groups are at par.
What's after 4th chapter? What extra?
So I have taught you whatever I have taught you. In that, you just don't have multi-components. The last lecture is not there, right?
Gibbs-Duhem equation.
Gibbs-Duhem equation is there, right? Those things are there. So the last class, where I started with phase changes, Raoult's law, where I started.
Yes.
That one. Sorry? So that's roughly, I think, 20%. And that's what we normally do. But 20%. Okay. I think that right. When I'm feeling it's like too dark. Okay. So I had not done a few things which the other group has done. So we'll just do those topics today. And some of them I had not planned, and some of them I had thought that I'll do later when we come to equilibrium. But anyway, so let's just finish those things, and then I have some questions for you which we can solve. Right. So now you all, so the one of the topics is about this Raoult's law. And you've all seen that the chemical potential, right, or the Gibbs free energy was given as the Gibbs free energy at a standard pressure plus RT ln T, or P by that standard pressure, right? So what would happen? Let's convert this into chemical potential. Let's write that the Gibbs free or the chemical potential is equal to chemical potential at some standard pressure plus RT ln P. That I just put that dotted thing, so even if you don't write, it's fine, but it's there, which is roughly for all cases which we take to be 1 bar. Okay. Now the thing is, if I have a liquid, it's in equilibrium with a vapor. So whenever things are in equilibrium, the chemical potentials are equal, right? Delta G is 0 for things in equilibrium. So if that is the case, then we have pure liquid, liquid A is equal to, so the chemical potential of the liquid would be equal to the chemical potential of the gas. So this is the chemical potential of the liquid, and on the right hand side of this equation I write the chemical potential of this gas. Yes.
Pure.
Pure. So we have a pure liquid, we have pure vapor, right? Chemical potential of the liquid is equal to chemical potential of the gas. If I add some solute, Okay. If I add some solute, then the chemical potential of the liquid, I'll write it like this, right? And the chemical potential of the vapor would be plus RT log whatever the new pressure is. And I can get rid of the standard chemical potential by combining these two equations, and what I would get is mu A is equal to mu A star plus RT log mu of liquid, right? RT log PA by PA star, and which according to Raoult's law is nothing but the mole fraction. So in general I can write mu A is equal to mu A star plus RT log of XA. So what it says is that the chemical potential of an impure substance, of a mixture, of the chemical potential of species A in a mixture is lower than that of pure A, because this is a negative quantity, right? XA is less than 1, so log of XA is a negative quantity and the chemical potential is lowered. The consequence of this thing can be seen over here. So if I plot chemical potential as a function of temperature, then I have already seen that the slope would be negative of entropy. I have seen these three regions: solid, liquid, gas. And if I am going to add some solute to it, the chemical potential is lowered compared to the pure liquid. So now the curve or the line for the liquid would be lower. Right. So if this was the boiling temperature and this was the melting temperature for this particular liquid, in the presence of a solute, the boiling temperature shifts to a higher value and the melting temperature shifts to a lower value. Right? And these are just related by an equation: delta T is equal to K times XA. Right? You could convert it into the form of molality of the solute.
A is a solute. A is a solute.
Sorry. XB. Right. So this K could be for the depression of the freezing point or elevation of the boiling point. Cryoscopic and ebullioscopic measurements, but you can convert this into molality instead of mole fraction, and then you would get the cryoscopic constant or the ebullioscopic constant. The same equation written in terms of molality. Molality of B. So that would be delta T is equal to K times molality of B. So for anyway, this is something which you have already encountered, and gas does not have the solution. Into the gas. Let's say I have added sodium chloride to water.
B is the solute.
B is the solute, right?
Then we have their partial.
Then they will, right?
Then the graph of gas.
But in that case also, right? Then of course the graph for the gas would also change, and then anything can happen. We've already seen that.
Partial pressure of the gas. Partial pressure means there must be some other gas molecules that are getting the partial pressure.
No, I'm referring to this fellow over here. The pressure of, it could be that the partial pressure of the gas, of the other gas, right? So, wait. This is not YA, as we have seen earlier. This is XA, right? I'm not talking of the difference in two gases over there. I'm just talking of if there is a solute present, then what would be the pressure of gas A, right? You're confusing between things in the vapor phase. Right? And of course, we've already seen actually in the case of volatile solutes, the partial pressure can change. We've seen curves that have a minimum, we've seen curves that have a maximum. Okay. So this is one thing. I think they also told that this delta T is equal to or simply K. Just one moment. RT square by delta H of the transition. XB is the mole fraction of the solute. Okay, so this is the starting temperature. Normally, I think in the book it says T star.
The normal volume.
The normal boiling or melting point, whatever. Okay, so this is something which has been told in the other class, so I should just tell you this.
This is the case with mole fraction of molality.
To the mole fraction. To the mole fraction. With a mole fraction. Okay. Now, this one you can get if you know the Gibbs Helmholtz equation, which is another thing I had reserved for equilibrium. But anyway, since the other class knows, let me just do it quickly for you. The Gibbs Helmholtz equation I guess that's the spelling. The equation is like this: del by del T of G by T at a constant pressure is equal to minus H by T square. And the derivation is fairly straightforward. All you need to do is differentiate by parts. By parts, yeah? Multiplicative rule. So let's consider T constant, del G del Tp plus G constant. I can write a complete differential for this fellow, right? Because it's dependent only on temperature. Temperature is dependent only on temperature, nothing else. So what I would get is 1 by T, right? Del G by del Tp is minus S, and this is G, sorry, minus, right? I've just taken one T common outside, right, which is equal to minus 1 by, sorry, why to keep the minus sign outside? Okay, I can keep a minus sign outside. S plus G by T, right? Del G by del T is minus of S. The minus sign there. And G is equal to H minus Ts, or H is equal to G plus Ts. So that means is equal to minus 1 by T into H by T. So that's what the Gibbs Helmholtz equation is. So this is very important when you consider equilibrium situations and you want to link the thermodynamic quantities to equilibrium constants. For example, the equilibrium constants that you find, the K equilibriums. I would have come to this later, but anyway, just because the other class knows, so you should know this. And you can actually use this equation to calculate that constant K. Right? We'll not go into that. I mean, I'm not of the opinion that we should do that part. Okay. The other thing which I actually left out, but since the other class is done, we'll do that also. The derivation of the phase rule. The phase rule. F is equal to C minus P plus 2. Since they have done it, so I better do it, right? The question paper is common. Okay? Huh? See, I don't know. They've done it, maybe they've done the depression in the freezing point and they've evaluated that. I don't want to do that part because I don't want to emphasize much on colligative properties. And no, whatever we have in the exam will be all common syllabus. Right? But the phase rule, I think maybe we should do it so you'll get some intuitive ideas. Okay. Okay, so let's say we have two phases, alpha and beta phase. Okay, and I guess this much I have done, but anyway, we'll just revise it again. So I have the chemical potential of phase alpha, and it has some pressure and temperature, is equal to the chemical potential of phase beta with some pressure and temperature, right? If these two phases coexist, okay, then the only two variables that I can vary are pressure and temperature for this thing. So I have a single phase system, let's say, and I can vary only these two things, pressure and temperature. And this is like, I have one equation over here, right? And this equation correlates pressure to temperature. So which means I can actually not vary two of them at will, but if I vary just temperature, pressure would be governed by this particular equation, right? So the degree of freedom, the freedom to vary independent variables is just one in this case. Okay. And this is not just for single component systems, but this is also true that the chemical potential of each and every component across the phases must be equal in equilibrium. So I can actually write that this could be the jth component. So for each and every component, the chemical potential must be equal. That's the definition of the equilibrium. Okay. Now, if I consider three phases, alpha, beta, gamma, let's say, then what I would get is mu j of alpha, pressure, temperature, is equal to mu j of beta, pressure, temperature, is equal to mu j of gamma, pressure, temperature, right? This is not one equation, but this is actually two equations. This equals this and this equals this. This equals this is dependent, right? So it doesn't matter. So now I have two equations relating pressure and temperature. So which means I can have only one value of pressure and one value of temperature for that. Of course, these equations have to be independent of each other. Which means I cannot have both the equations with the same slope and intercept, right? Overlapping. I cannot have both the equations overlapping. So if that is the case, then my degrees of freedom come out to be 0. Right? I have two equations, I have two unknowns, everything is solved. In the first case, I had one equation, two unknowns. Okay. Now, for 4 phases, if I think of 4 phases, then I cannot find 3 equations which can actually satisfy 2 unknowns. So what I'll have is alpha is equal to beta is equal to mu j alpha is equal to mu j beta is equal to mu j gamma is equal to mu j delta. That is what I'll have to write. That means I have 3 equations. So 3 equations, 2 unknowns. If all these 3 equations are independent, then they'll never satisfy. If one of them overlaps, then of course it will satisfy, which means I don't have 4 phases. Right? Which means I have 3 phases. So such a situation cannot arise. I cannot have 4 phases all existing together.
So please explain that the second line and the next line.
This one? So I have 2 equations over here and 2 unknowns. Right? So y is equal to mx plus m1x plus c1, y is equal to m2x plus c2. So if I have 2 equations, I can get it.
So why can't you have all 3 equations?
It can.
Common point.
It can be there, but the thing is that all of those would not satisfy these 2 unknowns at the same point. You can try this. You know, I could have two equations, right? And 2 unknowns. And the third equation, I can have a third equation which does not satisfy. Okay. So that's just things apart. But now think of a general case. And let's account for the number of variables that we have. Okay. So first things, we have 2 variables definitely. So let's say the general case. So P and pressure and temperature, that equals 2 variables. These are the 2 things that I can vary. Okay. Then I have to worry about the composition. Okay. So if I have C constituents, total number of constituents as C, then I can specify the entire composition of the mixture by C minus 1, right? C minus 1 variables. Yes? No. If I have C components in a mixture, I can specify the constitution of the mixture by C minus 1 variables. That is the mole fractions of C minus 1 variables, because the total is equal to 1. So I have then C minus 1 variables. This is true if all of them are in one phase. But if they are in a different phase, their compositions can vary. Right? So for each and every phase, I'll have to specify C minus 1 components, which means this becomes P into C minus 1. Right? So what we have is total P into C minus 1 plus 2. Yes? Oh. Okay. I have C components and I have to specify their composition. Right? So all I need to specify is the mole fraction of C minus 1 components. Yes? Because the total of the mole fractions is equal to 1. And now, if there are P phases, I have to specify these mole fractions for each and every phase. Right? So that means I have to specify P into C minus 1 variables. Plus 2 is anyway temperature and pressure. So I've just added the total. Right? Now think about equilibrium. At equilibrium, if I consider component J again, the chemical potential of all the phases would be equal. Yes? Which means I have P minus 1 equations for each and every component. Right? है ना?
So how can we say that each component will have 3 phases? Different components can have different number of phases. So how can we take them to be equal?
So see, I have some number of components. I can take an example of salt in water. So water would have some component in the vapor phase, but salt will not have any presence in the vapor phase. Right? So all I'll say is that X, the mole fraction of salt, is 0 over there. Right? So I actually what I do is make a general statement, and then later on if something is 0, I just remove it. So now I have P minus 1 equation here, governing all of them. And since I have C components, I'll have C times P minus 1 equations. Right? I'll have for mu I, mu j, mu k, mu l, so on and so forth, I'll have P minus 1 equations for each of them. And each equation means that I have to delete 1 degree of freedom. Yes? So which means I have to delete C into P minus 1 degrees of freedom. So I had so many variables that I could vary freely. Now I have to remove this, because these are the variables that I cannot vary freely. These become dependent then. And now if I add all this together, PC minus P plus 2 minus CP plus C just gives me C minus P plus 2.
equations and one solution.
They can be.
Three equations and one solution for it. The four phases, three equations will be there. One solution can be there.
So, huh?
They can exist. With some pressure or temperature, they can exist.
What phases? Okay, so that's the phase rule essentially. And this is what you use if you want to calculate the degrees of freedom. Now it's very important to count the number of phases, the number of components. Okay. And sometimes it can get tricky. So the number of components is equal to the number of chemically distinct species. Okay. But still this is not a complete description, as I will show you in a moment. And a phase is of course defined as a homogeneous, chemically and physically homogeneous phase. I don't know. Yeah. The recursive definition, yeah. I like that GNU. Anybody's heard of GNU? JNU. No, you guys, none of you is a computer freak? GNU is a free software distribution license. It says GNU and it stands for GNU is not Unix. These kind of things are like recursive acronyms. Okay. I should circulate this. Right. So what we have then is how best to define the number of components. I could give you some examples, and one of the favorite examples which I have seen is the decomposition of ammonium chloride, which is a solid, and it decomposes reversibly into ammonia gas plus HCl gas. Thermal decomposition. So we need to heat it. Okay. Now, I ask you, how many phases are there? 2 phases. Achha, remember one thing. Gas is always one phase. There you can't make a mistake. Okay. Gas is always homogeneous. So gas is always one phase. Liquids, there will be miscible, there will be immiscible. We can have different number of phases. Solids, of course, we can have different number of phases. Okay. But gas is always one. So we have 2 phases over here. One solid and one gas. Okay. How many components are there? 3 components are there. Right? But, although we see that there are 3 components, it's actually not. The thing is that the amount of ammonia and HCl happens to be equal. Yes? So if I specify the mole fraction of HCl, I would be specifying that of ammonia as well. That doesn't change, remains equal. So I cannot vary that at will. Remember, the degrees of freedom is C minus P plus 2. So if I have more components, I can vary more degrees of freedom. So this is just 1. But then, it just depends on how much of ammonium chloride dissociates. So it depends on the amount of ammonium chloride also. Which means all the three are related. So essentially I have only one component over here. Okay. I would count this only as one component. If I want to correct. Sorry? Yes. Yes. So I know how much I started. I know how much amount of ammonium chloride I have. Yes. And then everything is related to that amount.
Every time different components will be concentration of the atom. So we will never consider the product.
Oh, okay, you could consider just ammonia gas for that matter. Ammonium chloride would depend on that. So equilibrium, reversible equilibrium. Yeah. Not necessarily. Now, let me just tell you that. Let me add some ammonia from outside into this system. It's still an equilibrium. Right? But now the amounts are not related. If I have added some ammonia other than whatever was present here, if I add some external ammonia to it, then I have to account for one more component. Or if I have added some external HCl to it. Right? Yes, so a new equilibrium will be formed, right? Either way. That's why the number of components increases too. My degree of freedom changes. Right?
Please again explain this why NH3, HCl and NH4Cl all together are considered one component, although they are
because what I want to define over here by NH3 and what are the degrees of freedom that I can define? That is the mole fractions. And the mole fractions of all of them are related. Right? The mole fraction of HCl and NH3 are the same, and the mole fraction of if we affect the equilibrium, then of course, then I say that C would be equal to 2. Right? If I have added some HCl from outside, then of course C would be add HCl or NH3 from outside, C is 2. Right?
please again explain that.
But in this case, I want to define the mole fractions, right? If I know the mole fraction of this fellow, I know the mole fraction of this and of this.
But these are in different phases, so how can we different effects?
I started with some amount of NH4Cl, right? So it's very important, right? So I started with some fixed amount of NH4Cl and I heat it, right? And now I know how much amount of NH4Cl do I have, right? If I know that, I know how much amount of HCl I have, how much amount of ammonia I have. Yes? I don't have to specify the mole fractions of all the three separately. Okay?
So if we add NH4Cl, only NH4Cl, so then the equilibrium function will be affected.
Then it won't be. So that's why I said only HCl or NH3. If I add NH4Cl, then I'm again bringing it back to the same equilibrium. So then of course, then still C remains to be 1. Okay, well, we can find a lot more of these kind of examples, but let's do some questions from the phases so that you're familiar with what we've done in the lectures is up to chapter 3, right? In the tubes, sorry. In the tubes we've covered questions up to chapter 3. Let's do some questions which are more reflective of the phases. Okay. So this is actually from one of the tutes from the other group. You can also get this. It's online, and also I guess it should be there in Scoops too. So it says temperature dependence of vapor pressure of solid sulfur dioxide can be approximately represented by the so vapor pressure of solid sulfur dioxide can be represented by the relation log P in torrs. The 760 torr is 1 atmosphere. 10.5916 minus 1871.2 by temperature in Kelvin. So this is solid vapor equilibrium, and then for the solid liquid and liquid vapor, it says log P again in torr is equal to 8.3186 minus 1425.7 upon temperature in Kelvin. You've already done this. You've done the Clapeyron equation, you've done the Clapeyron equation. Now which ones are these? Solid vapor and liquid vapor, right? So essentially if I draw the phase diagram, pressure as a function of temperature, remember which ones had a log in the expression? The Clausius-Clapeyron, right? So this is the one, and that's the other one. Yes? So the question says, estimate the temperature and pressure of the triple point of sulfur dioxide. Huh? Done it. How much is that? 190. Does it come from this, or do you know? Okay. So how would you do that? Estimate the Equate both the equations, right? So let's go another step forward. Estimate the boiling point of sulfur dioxide. Well, the question doesn't say, so let's say normal boiling point. Ready degrees C. Ah, 1 atmosphere. Sorry. Yeah, of course you can get the boiling point, right? Yeah, put 760 over there, right? Okay, let's go a step further. Heat of evaporation at the boiling point. Heat of evaporation at the boiling point, of course. Evaporation. Huh? So all you need to do is use the Clausius-Clapeyron equation, right? Exactly. You just need to, because that's also a log P equation, right? I don't remember, but it was delta H by R into 1 by T, no, T minus 1 by T star. Minus. So if I see this, this would be log of P is equal to log of P star minus, that should be the delta H by R. So there's another question which says, which gives you such things for zinc, vapor pressure of solid zinc, liquid zinc. It's just from one of the previous minors, right? But over here, there's another concept which I could just tell you quickly, and that one is, for example, log P in, that's in millimeters of mercury, doesn't matter, it's the same thing, 6850 by T minus 0.755 log of T plus 11.24. So that's a solid vapor, and then we have liquid vapor as log of P mm mercury is equal to minus 6620 by T minus 1.255 log T plus 12.34. Everything else is fine, but this fellow says calculate the difference in CPs, the specific heat capacity of solid and liquid zinc. A very slight trick over there. And the thing is that in the Clausius-Clapeyron equation, we assume that delta H is temperature independent. Right? Now, if we assume that delta H is not temperature independent and then integrate, then we would have delta H plus Cp dt. dH plus Cp dt would be the expression delta H. So the change in delta H would be delta H plus Cp times delta T. Right. If we use that, then we get the second term over here.
So people know the equation of Cp, K plus B versus
No, Cp you assume to be temperature independent. Okay, but so you can assume Cp to be, if you want to calculate the Cp over here, you can assume the Cp is to be temperature independent, but not the delta H. Yes? Delta H plus. So delta H changes as Cp times delta T, right? Cp is equal to delta H by delta T, delta H by delta T. Okay, the rest of the questions that are here in Tube 2 are for mixtures, so don't bother about that. I had another few questions. If people are still worried about work additional maximum, work maximum, and all those concepts. Still worried? Okay. Just fairly straightforward, so just write it down. So 1 mole of glucose is oxidized to carbon dioxide plus water. Just balance the equation 6, 6, and 6. And what you get out of this is the delta U for the reaction is equal to minus 2808 kilojoules per mole. Okay. Delta S of the reaction is equal to plus 182.4 joule per Kelvin. This is all done at 25 degrees C. The question is, how much of this energy change can be extracted as heat at constant pressure and work? We can assume the gas has to be ideal.
work at work additional or work maximum?
Maximum available work. Okay, QP. Great. It's exactly the same as delta H, and delta H is equal to delta N RT, delta N is 0. Right? And maximum available work. Yeah. What would be the equation that you would use over there? Delta U minus T delta X. Now, I did not say anything about constant volume over here, right? But it is constant, right? So if I ask you, what is the maximum additional work over here without calculating, can you tell me? Delta A is the maximum additional work because the volume is constant. So delta A when volume and temperature are constant is equal to maximum the additional work, right? It's maximum because it's anyway reversible. Delta G when pressure temperature are constant. Delta U when entropy volume are constant. Delta H when pressure entropy are constant. They are all equal to work additional. So what is delta G for this? Right. Delta H plus? That would be H plus PV. H minus TS. Okay. As long as it's resolved, we don't have to bother. Okay, another kind of, for example, let's think of some additional work. Let's think of a rubber band that stretches. Right. A rubber band which stretches and expands, right? Stretches and contracts. So what I would then, I'm just telling you how to write these equations, nothing more. So dg would be equal to vdp minus sdt, that was plus work additional, right? I could say that that is equal to the force times dl. Huh? Additional work, right? Non-expansion work. Right? I mean, this is something similar to that the change in number of moles that we've done. Likewise, I can get F is equal to dg dl at constant pressure temperature, right? I mean, all these, the same kind of equations that we've developed, we can apply to,
For mu.
we did the same thing for mu, right? Mu was equal to del Q by del N. So if you are given some additional, I mean, if you look up at Atkins, there are 3 or 4 different kinds of additional work that just specified in a table. I think it's in chapter 2nd. It says one is surface tension, one is the Hooke's law, the other, this is Hooke's law, right? The electrostatics, potential, right? Magnetic work. So those are the kind of things which you can think of as additional work. Of course, changing the number of moves. That's what the example is. Okay. So from your tubes, I have not been able to solve one question. If somebody has solved, maybe we can share. dq reversible by t, the cyclic integral. Huh? I mean, I can solve it for a given system. Huh? Maybe that was wrong. No, I got stuck somewhere with that. If I want to use the Euler's technique, yes. If I want to do it graphically, yes. But those are specific systems. So if somebody gets a solution to that, let me know. Otherwise, anybody has any problems with any of the tubes, any of the questions? We can do that now. Okay, let's switch this off.